Welcome back. Section 4.9 Rank of a matrix. Consider a matrix A, A11, A12, A1n, A22, A21, A22 to A2n, all the way to AM1, AM2, AMn. That is, its size is m by n. The row space of A is the subspace of Rn spanned by the rows of A. R sub n is the the vector space of rows of size n. So you see, this row has size n. This row has size n. So there are m rows, each of size n. Consider the space spanned by these rows. That's called the row space of A. Likewise, the column space of A is the subspace of R super M. So look at the columns. Each column is of size M. So take these columns of our matrix A. The space spanned by the columns of A is called the column space of A. Theorem. If A and B are two m by n row equivalent matrices, then the row spaces of A and B are equal. Similarly, if A and B are two m by n column equivalent matrices, then the column spaces of A and B are equal. So I hope you understand, you recall the meaning of row equivalent matrices. That means one matrix is obtained from the other using elementary row operations. Likewise, to be column equivalent matrices, one matrix is obtained from the other using elementary column operations. So, if one matrix is obtained from the other using elementary row operations, then the theorem says the row spaces have to be equal. Likewise, if one matrix is obtained from the other using elementary column operations, the theorem states that their column spaces are equal. Proof. Let A and B be two m by n row equivalent matrices. That is, B is obtained from A using elementary row operations. Okay? The rows of B are obtained from the rows of A by using elementary row operations. That is, the rows of B are linear combinations of rows of A. That's the elementary row operations. What are the elementary row operations? Either you interchange the rows or multiply a row by a number or take a combination of one row with the other. Either way, B is a linear combination of the rows of A. Rows of B are linear combinations of rows of A, which means linear combination of rows of B are linear combinations of rows of A, because rows of B are anyway linear combinations of rows of A. So further linear combinations of rows of B is nothing more than linear combinations of rows of A. This implies row space of B is contained in the row space of A. I hope this is clear. Linear combinations of B, rows of B, that is row space of B. Well, a linear combination of rows of B is a linear combination of rows of A. So row space of B is contained in row space of A. Recall, elementary row operations are reversible. Remember, elementary row operations are just basically matrices, invertible matrices. What about the reverse of these elementary operations? They are also elementary row operations. In other words, rows of A can be obtained from rows of B using these reverse operations, reverse elementary row operations. Therefore, rows of A are linear combinations of rows of B. Again, linear combinations of rows of A are therefore linear combinations of rows of B. Thus, the row space of A is contained in the row space of B. So notice row space of B contained in row space of A. Row space of A contained in row space of B. The only way this is possible are they are both equal. One contained in the other and the other contained back in the first. The only way this can happen is that they are equal. Proof for column spaces, it's identical. It's the same argument. Instead of using elementary row operations, you are using elementary column operations. Proof is identical. Let's look at an example. Find a basis for the subspace V of R5. R sub 5 means row space of dimension 5, right? Spanned by, here is our 4 vectors v1, v2, v3, v4. They span a subspace, right? So find the basis for that. What do? Consider the matrix formed by these 4 rows. Use elementary row operations. Assuming our calculation is correct, this is the reduced row echelon form of A. So notice, how do you get reduced row echelon form? By doing row operations on these. So the row space here will be equal to the row space here. Alright. So notice I have an entire row of 0. But otherwise I have 3 vectors which are non-zero in my reduced row echelon form. By the theorem we just proved, row spaces of A and B are equal. The first 3 rows of B are linearly independent because the leading ones are in different locations. You can check. These 3 are linearly independent and therefore rows of reduced row echelon form are linearly independent. Rows, not all rows, non-zero rows, which means the basis of the row space of B is the set W1, W2, W3, where W1 is this, W2 is this, W3 is this. What are these W1, W2, W3? That is W1, that is W2, and that is W3. So B has these 3 non-zero rows, therefore they span. Now notice these W1, W2, W3 forms a basis for the row space of B, which is equal to the row space of A. Note importantly though, this set is not a subset of your original S. So you see, none of these are from the original 4 rows. So we found a basis of the row space which is not a subset of the original set. Okay, that's important to note here. But what is an advantage of this basis? Take any vector V from the space, row space. 5, 4, 14, 6, 3. All right. Now notice this 5 is from the leading one. So you can say 5W1. After that, this 4 comes from W2. So 4W2. And then notice I have location here at 4th. So that's at 6. 6W3. So it's so simple. If you use reduced row echelon form, the rows are such that you can immediately see from a vector what the coefficient should be. Okay, you can check for yourself. Procedure to identify a basis for column space is similar. What do? Use elementary column operations to obtain column echelon form. Okay, reduced. In one of our previous sections, we found a way to identify a subset of S, that is a basis. So remember, we could always reduce a spanning set to a basis. How do we do that? Start with this combination equals 0. A linear combination equals 0. A1 times the first vector, A2 second vector, A3 third vector, A4 fourth vector equals 0 vector. That gets us a system, a linear system. Okay, assuming my calculations are correct, I get this system. I have 5 equations, 4 variables, right hand side is all zeros, which gives me an augmented matrix. Look at the augmented matrix. I claim it is A transpose. Why? Look at that. 1, -2, 0, 3, -4. You see? Likewise, 3, 2, 8, 1, 4. Okay? What is this? Why is this A transpose? Look at A. If you remember, A is made up of these rows. So instead of this row, I have it as a column. Notice this. 1, 2, negative, 1, -2, 0, 3, -4. That's that column. So you see, if you remember what we did earlier, A was made up of these rows, right? Whatever vector you got. Now the augmented matrix, on the other hand, has those rows converted to columns. That's why it's A transpose with the 0. All right. Reduced row echelon form. Do everything you can, you get this. Now here you see, remember our goal is to find a basis that is a subset of your original set. I have non-zero leading ones, column 1, column 2 and column 3. Okay, which means V1, V2, V3 is the set we are looking at. So, summary. To find a basis of the row space, start with the row vectors. One approach, form a matrix, transform it to row reduced echelon form, reduced row echelon form. Set of non-zero rows will form a basis of A. This basis will not be a subset of S. Approach 2, consider A transpose. Transform it to row reduced echelon form. Identify columns with leading ones. Those will identify vectors from your original S which form a basis. Okay. Now this is for row space. Column space, consider the column vectors of A. One approach, transform A transpose to its. Why? Why do I do this? You see, I'm looking at columns of A, right? So build the columns rather than converting using elementary column operations. If you take its transpose and use row operations, it comes to the same thing. The transpose of the non-zero rows will be a basis, you see. So instead of using elementary row operations, you can use elementary column operations. So use the transpose. Another approach, if you want to find a subset of this, take A itself, do its elementary row operations, identify leading ones, that will give you a basis. Okay, so notice this is for column space. In both cases, you are looking at A and A transpose for column space or for row space. Okay, it's the difference is in row space for approach 1 you are using A, approach 2 you are using A transpose, whereas for column space approach 1 use A transpose, approach 2 use A. Okay, let's continue in the next video.